Hi class, I'm going to be discussing Slater's rule, its effective nuclear charge. This is under 9.2. Dr. Christensen has already covered a portion of effective nuclear charge and has worked out problems regarding this, and there's a problem posted at the bottom of Canvas that he discussed in lecture. However, Slater's rule is another way to calculate effective nuclear charge, and he did not cover that. So these are just a few slides showing you how to do how to calculate effective nuclear charge this way. So Slater's rules for calculating shielding is an S, and it is the same equation that is listed in 9.2. This is equation 9.1. The Z with the F, this means effective nuclear charge. The Z is the atomic number and S is for shielding. Valence electrons do not shield or screen as efficiently as core electrons from the nucleus, the protons. Valence electrons in N energy level contribute a value of 0.35 towards the shielding, and core or inner electrons contribute a value of 0.85. This is very different from the way that Dr. Christensen has discussed it in his lectures. Not very difficult, but is definitely different, so you should know both ways. So to determine the shielding, you take the valence electrons that you count, and you always, and I'll cover this right now, multiply that by 0.35 plus the core electrons, the number of core electrons, and you multiply that by 0.85. This gives you your shielding. You subtract it from the atomic number, and that is your effective nuclear charge. Now, the one thing I want to point out when you're dealing with valence electrons, say you're pinpointing on one of those valence electrons, you do not count one electron out of all those valence electrons because that's the one you're considering. So you count everything but that one. So here's an example. Oh, this moved over, sorry. We have sodium. Sodium has an atomic number of 11. So if we do the electron configuration, everything that's underlined would be considered core electrons. And then you have one valence electron. But because this is the valence electron we're focusing on, we don't count it. So it's always 1 minus from the valence electrons. So we have 0 for the valence electrons, and then we have 10 core electrons. And you multiply that by 0.85, which gives us a number of 8.5. We plug that into the effective nuclear charge, subtract it from the atomic number, and it gives us a positive 2.5. Now, with magnesium, which is right next to it, is an atomic number of 12. This time we have 2 valence electrons, but we're only going to count 1. So think of it again as we're focusing on 1 valence electron out of that, and we want to count the other valence electron or other valence electrons that are there. But the one that we're focusing on does not get counted. So in this case, we do count 1 of the valence electrons because there's 2 of them. Multiply that by 0.35 plus 10 times 0.85 because there are 10 valence core electrons. And that gives us a number of 8.85, just a little bit more than sodium. Plug that in, and it gives us a plus 3.15. So magnesium has a higher effective nuclear charge than sodium. And here's just a visual. So if we're looking at sodium, if we want to know the effective nuclear charge of sodium, then we don't count this one because this is the one we are, in a sense, looking at. So we count everything around it. So that means there would be nothing. That's what accounts for the 0, is that since there's only 1 valence electron, we're focusing on that one, we put a 0 for the when we do the multiplication for the valence electrons. Now over here we have 2. So we remove 1 and we look at it from the point of view of this electron so we can count the other electron. And that is why you have, going backwards, the 1 here in place. Okay, so calculate the effective nuclear charges experienced by valence electrons of potassium and calcium. Now these are under Slater's rules, and if you were given this, it will definitely state it's Slater's rules. If it doesn't, then it will default to the way that Dr. Christensen has shown it. Okay, so use Slater's rules to calculate the value of shielding and then subtract and handle this problem. So here's potassium. So it has 1 valence electron. The rest are core electrons. So we're not going to count this one. Same rules apply. So it's a 0. So we're only focusing on the 18 core electrons, which gives us a number of 15.3. Subtract it from the atomic number of 19, and it gives us a plus 3.7. Now calcium has 1 more electron, so we anticipate that it should be a larger number, and it is. So we go through the same steps, but we count one valence electron. So unlike this one that we didn't count anything, now we have to take this into account. And this gives us a number of plus 435. So for each valence electron in calcium, atom experiences a stronger effective nuclear charge than the valence electron in potassium. So basically it's got a higher number. So it's got a stronger nuclear, it's a tongue twister, effective nuclear charge than potassium. Okay, that's it. Thank you.